Assalamualaikum warahmatullahi wabarakatuh, and hi to Dr. Aidin and my fellow friends. Today we will have a presentation about partial differential equation application. We are from group 4, and my name is Anaki Hakim bin Muhammad Khairi, and our members consist of Aiman Rais bin Zulkifli, Ahmad Ashraf bin Azhar, Eugen Tiran anak lelaki Guna Segaran, and Ruben anak lelaki Pacaipan. Moving on to the introduction, so what is PDE or partial differential equation? So in terms of definition, a partial differential equation (PDE) is a mathematical equation that involves multiple variables and their partial derivative. It describes how a multivariable function changes with respect to its variables and their rates of change. And then for the industry, we have specified the use of PDE in heat transfer. So, why heat transfer? Heat transfer plays a very crucial role in various industrial processes such as manufacturing, power generation, and mechanical engineering. The function is to analyze and predict heat transfer phenomena accurately. PDEs are commonly used. So, for the industrial example, we have chosen the company Body Code. So, Body Code is a company that specifies in use of heat transfer. It uh, serves various things that you can do with body code, such as case hardening with subsequent hardening operation, case hardening without subsequent hardening operation, hardening and tempering. So, what is heat treatment? Heat treatment is a controlled process used to alter the microstructure of materials such as metals and alloys to get the desired characteristic that we need, such as to harden the material or make the material that can bend a little bit more than usual material. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. Now my name is Samar Ibn Zulkifli. My metric number is 14806. Now I will explain about application of heat transfer. So where is the formula is we use? As we can see, there are three formula, but I won't go detail about that because my friend in next slide will tell you all about it. But I will tell you where it we use. It used in heat conduction, heat convection, heat transfer, heat flow, and radiation. Okay, to give more explanation about it, I will give one example, and it is at metal casting process in manufacturing industry. So consider a metal casting process where molten metal is poured into mold to form a solid object. The goal is to ensure that the solidified metal has uniform temperature and solidification throughout the casting. By applying the dimensional heat equation, we can model and analyze the temperature distribution during the solidification process. By solving the dimensional heat equation numerically using technique like finite difference or finite element method, one can simulate the solidification process and predict the temperature distribution and solidification pattern within the casting over time. This information is valuable for optimizing the casting process, determining the cooling time required, identifying potential defect, and ensuring the final product meets the desired specification. Okay, that's all from me. Thank you.
Good day, doctor. So my name is Eugen Tiran. My matrix number is 217846. So today I'm going to explain about engineering applications of partial differentiation equation. So today is going to based about one-dimensional heat equation. So the first one is the one-dimensional partial differential equation is du dx equals to alpha square d2u over dx square. So steady temperature on the rod is u equals to b minus a over length times by x plus by e. So the correct solution of 1D heat equation is stated below. So I'm going to further explain based on the example on the next slide. So now in this slide we will look further into the example of partial differential equation. A rod with 30 cm long has its end A and B at 20 and 80 degrees Celsius until steady state condition. The temperature at each end reduces to 0 degrees Celsius and keep it so. So find U in terms of X and T. So based on the diagram, we can see that's a rod with a 30 cm length with initial temperature of 20 degrees Celsius and a final temperature of 80 degrees Celsius. So based on the before temperature change, as I explained in the slide previously, we can use the equation which is U equals to B minus A over length times by X plus by A. So we can substitute the value of initial and final temperature and the length of the rod. So we can get final equation which is U equals to 2x plus 20, which is to find the initial temperature before the endpoint reduces to 0 degree Celsius. So to find the after temperature change, we can use the one dimensional equation which is du over dx equals to alpha square dtu over dx square. So I'll explain further on the next slide. Thank you. Okay, so for the third slide, so we have three boundary condition. So the first one, second one, and third one respectively based on this slide. So based on this slide, we can substitute the values in the equation, the correct solution equation, to find the value of u and t respectively. So further explanation based on the solution will be explained by my team member on the next slide. So that's all from me. Thank you very much.
Okay, as we all know, there is a three boundary condition. So first of all, we can apply the first boundary condition and make it x equals to 0, which refers to the initial point, the end point of the rod. And we all know that the temperature of the end point, we need to make it equals to 0. So when we make the equation when we substitute x equals 0, we get the equation c multiplied by e power negative alpha square p square t. And when we make it the equation equals to 0, we get that the value of the c is 0. After that, we can substitute the value of c in the equation number 1, and we get that the equation is u equals to d sine px multiplied by e power negative alpha square p square t. After that, we can apply boundary condition number 2. So boundary number 2, which means u x t equals to d sine pl multiplied by e power negative alpha square p square t. So we make it x equals to l, which means l is equals to dcm. That means the end point of the rod. So we all know that the first point and the end point of the rod, we need to make it equals to 0. So we make the equation equals to 0, and we get that we can let that sine pl equals to 0. And we all know that there is a term where sine n pi is equals to 0 and cos n pi is equals to negative 1 power n. So we can equate that sine pl equals to sine n pi, and we can make it p as a subject and p equals to n pi over l, and we can substitute the value of p into the equation where we get u equals to d sine x n pi over l multiplied by e negative alpha square n square pi square over l multiplied by t. Okay, now the next part is, we all know the most general solution I've stated before is u equals to sum of n minus 1 to infinity pn sine n pi x over l multiplied by e power negative alpha square n square pi square over l multiplied by t. And then we can let that bn is equals to d. So after that, we can apply the boundary condition number 3, where at the initial temperature, we found that, as Eugene didn't stated before, we found that the equation is 2x plus 20. So we can make it a general equation u equate with 2x plus 20. After that, our main objective is to find what is the equation for bn. So to find bn, we can use the formula where it goes by 2 over l integrate 0 to l fx sine n pi x over l to dx. After that, after integrating, we get that we can integrate using we can separate it, and we use this method to integrate the complex integration. After integrating, we get that bn is equals to uh, 2 over n pi over l multiplied by l in bracket negative 2 power 2l plus 20 multiplied by negative 1n plus 20 cos 0. And then we know that the value of L is 30. So when we substitute 30, we get that Bn is equals to 40 over n pi in bracket negative 4 um, times with negative 1 power n plus 1. After that, we can substitute the general we can substitute Bn in the most general solution, and we get that uxt equals to sum of n minus 1 to the infinity 40 over n pi negative 4 multiplied by negative 1 power n plus 1 multiplied with sine n pi x over L multiplied by e negative alpha square n square pi square over L multiplied by t. So this is the most general solution where we need to make it the rod at the end point of the rod is equal to 0, equals the temperature equals to 0. And if we want to find any point of the rod, we can just substitute in the formula and we can find the temperature. Yeah, that's all from me.
Hello, today I would like to share about conclusion of partial differential of heat transfer. In conclusion, the heat transfer which is partial differential equation is fundamental tool used to model heat transfer in solid material. It describes how temperature diffuse through a medium over time and is based on principle that the rate of change of temperature at any point is proportional to the second derivative of temperature with respect to position. In summary, heat transfer is to analyze and predict temperature change in solid material, thereby aiding in the design and optimization of various heat-related processes and systems. Heat transfer is distributed and transferred with a system. First, design efficient heat exchangers, optimizing thermal insulation, predicting temperature profile, ensuring safe operating condition. Partial differential equation of heat transfer also commonly used in industry such as energy production, manufacturing, chemical processes, HVAC, automotive. So, partial differential equation is important for understanding and optimize thermal process, leading to improved energy efficiency, enhance product quality, and increase safety in industrial operation. So that's all about conclusion of partial differential equation of heat transfer. Thank you.